Hello, welcome to your subject MECH 3. So we will start with your module 1, okay, which is simple stress. So under simple stress, we will be discussing subunits, okay, which are the type of simple stress actually. So again, this is introduced in our introduction, okay. So we have here the first type of simple stress. We call that one the normal stress. Okay, so in this unit, okay, of your normal stress, we will try to define again, okay, just to define again, repeat defining your simple stress, okay, for that to be clear to you, and then of course to compute for normal stress, and of course to define actually what is normal stress by having examples. Okay, so just a recall from your rigid bodies, okay, from your statics of rigid bodies. We will try to again recall the types of forces. We have what we call as the compression and the tension. Okay, so compression and tension. So the only difference here is that compression is a force which is trying to or tend to shorten or decrease a length, or it is actually just a force pressing, okay, towards a certain material. That is compression or compressive force. While tension is trying to elongate, okay, that is a force trying to elongate the material, or that is going away, a force going away a certain area. Okay, so those are the two types of our forces, compression and tension, or compressive force and tensile force. Okay, so that is important. We need to understand, or we need to recall those two types. And then we have here what we call another recall from your statics. We have what we know as the external forces and internal forces. Okay, so what are the difference of these two? Okay, if you say external, those are the force that is experienced by a certain material. Okay, that is an outside force that is experienced by a material, while this internal force, okay, internal force is a force that is acted by a certain material to resist deformation. Or let's say you are going to press a wall and then the wall will try to react. That is the internal forces. It will react, because if that will not react, then there should be movement or there should be deformation. Okay, there is a reaction, an equal reaction for that to be equilibrium, isn't it? There should be an equal reaction always to a force, so that there will be no resultant. Because if there is a resultant, then there should be a deformation. Okay, there should be an effect. So that is the difference of external, an outside force acted on the body, and the internal force is a force acted by the body, okay, against or to counteract the external force. Okay, so those are the simple recall. Okay, so you can read about this. Okay, so these are just to, okay, I will just explain this one in general. So if you will try to consider, okay, let's say this is a material, okay, or yes, this is a material. And then there are a lot of external forces. These are the force, these are the external forces acted on that. We have different. And if you try to recall your rigid, we have what we call as the collinear, coplanar, and so on and so forth type of forces, isn't it? So let's say they acted on different directions and different values. So of course that will have a lot of, you will combine that one and there will be an effect on the certain body that we are considering. So how are we going to analyze that one is we need to combine all the effects of this, since these external forces are acting together. Okay, so for example, I want to analyze the effect of those external forces within this area. I will try to cut that material and then try to expose that one, and let's try to see what happens or what is the effect of that on this certain area. Okay, so we will try to separate here. Then let's consider a very small, okay, very small part of that material in our cutting plane. Then in that certain point, okay, you can say that is a point, or that is a very small square. Okay, at that certain point in the material, okay, there are different directions of forces acting on that because of these different forces. Okay, different direction of forces. So we can break this down. Since this is a three-dimensional, okay, we can break this down in a three-dimension. We can say x, okay, on axis x, axis y, and then axis z. Okay, then because of the different direction of external forces, there will be a resultant force at this point, which is going to X, a resultant force that is going to Y, and then a resultant force a component of resultant force going to X, Y, and Z. Okay, because again, we do not know yet the actual direction of that, but even if there is in an actual direction, if you will combine all these external forces, then we are not sure if that is directly going to X, directly going to Y, directly going to Z. So let's assume that there are parts or components of that is going to X, Y, and Z, and then if we will try to combine all these components, isn't it? Okay, we have what we call as components, and you can combine that one into a single resultant or a single force. We call that one the resultant. Then that will be our delta F. Okay, that delta means small force, since we are just considering here a small area. Okay, so that is the meaning of that. So the external forces, okay, that will be combined together will have a combined effect on a certain point within the material. And how are we going to analyze that one? Then we will be separating it into components X, Y, and Z, and then after we have all of these components, then we can combine this into a single resultant, and that is the certain force that is acting on that certain point on the material. Okay, so that is how an external force will affect a certain material or a certain body. So the question there is, we have discussed these stresses on, or definition of stress on the introduction, but there are a lot of stress. There are 4 that is actually discussed in the introduction: the normal, the shear, the bearing, and the thin wall pressure. Okay, so how do we know? How do we know if what type of stress that is being experienced by that certain material within this type of external forces? So how are we going to know that one? Is of course we are going to analyze it separately. Okay, let's try to find out if there is a normal stress, if there is a shear stress, if there is a bearing stress, or there is a thin wall pressure. Okay, so that is how we will be doing. We will try to divide the forces, and then we will try to analyze. So this unit is only to discuss, we will try to focus first on normal stress, or what is normal stress. So again, we just discuss here what happens on a certain point. We are considering a certain point. Okay, so simple stress. Okay, again, we will try to define. Simple stress is the condition under which the stress is constant or uniform at a section within a body. Okay, so that is simple stress. Okay, so the condition under which the stress is constant or uniform at a section. Okay, that is what we call a simple stress. Because if you want to level up the topic about stresses, we have what we call as the stress tensors. Okay, that is a 3-dimensional analysis. But for us, since we are just starting on stresses, we will try first to focus on a plane or simple stresses. Okay, so simple stress muna tayo. So we are referring to a simple stress if the stress is constant or uniform or the same at a given section. So if you will try to cut that one, or at the plane, the stress acted on that is experienced by that area or plane should be uniform, so that we can consider it a simple stress. So we will try to limit first ourselves to that type of stress. Okay, later on, if you will go on your higher mechanics, then you will have the 3D dimensional or the stress tensors. Okay, so in many load carrying members, the internal action on an imaginary cutting plane consists of either only the axial force, or we call that one the normal force, or only the shear force. Okay, examples of such element includes cables, okay, simple truss members, centrally loaded brace rods and bars, bolts, pins, rivets connecting to members. Okay, so those are just examples of actual application of simple stresses. Okay, if the type of stress experienced by that certain material is simple, then that will fall under simple stresses. The analysis will fall under simple stresses. If that is purely shear stress, if that is purely axial or normal stress, then that is a simple stress. Okay, so in this Okay, in these bodies, the values of the simple normal stress and shearing stress associated with each action can be approximated directly from the definition of stress and the conditions of equilibrium. So that is what we will be discussing on the succeeding examples. Okay, we will try to define when will that be normal, when will that be shear, when will that be bearing, or when will that be thin wall pressure. Okay, so we'll start. Okay, this is unit 1 and this is focused on normal stress. Okay, so the previous slide is just a recall and a general discussion on simple stress. Okay, so normal stress, okay, so it is represented by this equation. Okay, this symbol, we call this one sigma, a Greek letter sigma, and then P over A. What are these? Okay, if we say sigma, that is the normal stress. By the way, if we say normal, okay, we will later on discuss that one. We sometimes call normal stress an axial stress. Okay, I will explain that one later on. For in P there is the force, the internal normal force that is experienced by the material. Okay, that we are trying to analyze. And then the A there is the cross-sectional area of the material itself that we are analyzing, which is perpendicular to the force P. Okay, the force is perpendicular. Let's say this is the area, this is the force that is perpendicular 90 degrees with the area. That is a normal stress. That's why we call this one normal, because the angle is 90 degrees or perpendicular. So we call this one, we sometimes call this one, or we commonly call this one as axial stress. Axial. Why? Let's say this is the rod. Let's say, for example, this is the rod. If I will cut that one, the force is parallel to the axis of the rod. That's why we call this, we sometimes call this one as axial stress. Okay. So again, when do we have a normal stress? When the force is applied on an area which is perpendicular. Okay. So the area and the force is perpendicular or 90 degrees for the stress to be a normal or axial stress. Okay. So just a simple reminder. So how is that again? How to get the normal stress? Just divide the force, divide it by the area. So you will expect. That is the good thing in mechanics, because you can actually figure out what is that certain quantity by looking at the unit. That is how important the units of a certain quantity. So as you can see, P there is a force, A there is an area, so you will end up with the unit of stress or normal stress, which is force over area or force per area. So we will try to remind ourselves about these prefixes of our units. Okay, so if we say mega or M, that means that is 10 raised to 6. We have what we call, of course, before this, we have 10 raised to 3, that is kilo, which is K. Giga, which is J, 10 raised to 9, okay, and so on and so forth. There are a lot of that. We have also the negative exponent, the nano, and so on and so forth. Okay, micro, and so on and so forth. So 1 meter is 1000 millimeters. Just to remind ourselves, 1 foot is 12 inches. 1 kilonewton is 1000 Newton. Again, kilo means 10 raised to 3. Okay. So 1 kips, that is 1000 pounds. Okay. So just to remind ourselves on the units of forces. Okay, we will try to relate that one later on with the stresses. So that is the formula for normal stress, and that is symbolized by sigma. Okay, so we will now have an example. Okay, so example number 1. A hollow steel tube with an inside diameter of 100 mm must carry a tensile load of 400 kilonewtons. Okay, so determine the outside diameter of the tube if the stress is limited to 120 meganewton per mm squared or meter squared. So how will this be a normal stress problem? Okay, so let's try to write down. So that is an important step on problem solving. For you to analyze what is being asked, you need to write down what are given. So what happens here is that we are trying to refer on the figure. We'll try to refer on the figure the hollow steel tube, okay, which is in a shape of circular. It means hollow because inside is a space, okay, with this diameter of the space inside to be 100 mm. And we are using this to carry a tensile load. Okay, if we say tensile, that is a tension force. If we say tensile, that is perpendicular. Okay, perpendicular, of course, to this certain material or to this steel. And then we are going to determine the diameter of that. that. So what should be the diameter for that to be able to carry that 400 kilonewtons, given that it says there that we are going to limit, okay, or that is limited only to 120 meganewton per meter squared. What does that mean? That is the capacity of this certain steel, or this certain type of steel used in this hollow tube. Okay, so we should not exceed that one, so that this will not fail, or this will not rupture. Okay, the steel tube will not fail. Therefore, we will limit ourselves in a 120 meganewton per meter squared as the stress. Okay, and how do we consider this as a normal? Because the force is perpendicular to the steel tube. Okay, so we can now consider this as a normal stress problem. So again, what is the formula for that? But first, okay, let's go back. The formula is sigma is equal to P over A, so that we will know what to write down as the given. So we are given there the 100, that is the inside diameter. Okay, maybe we will deal with that later on, because in our formula what we have is area. So we will try to relate that one. How will that be related with the diameter? But first is that we are given here 400 kilonewton, which is the force. However, in our formula, P there should be the internal force. But in our case, that is the external. However, if you will try to recall your rigid, the material should exert an equal resisting force or reaction force to the external for that to be in equilibrium. Kaya, if your P there is an external, that should also be the internal. Okay, because there are no other force applied on that steel tube. So that should also be the internal. Okay, so your 400 here should be also be our P, which is the internal. And then we will try to limit ourselves on a stress, which is a normal stress of 120 meganewton per mm squared, or that is megapascal. Okay, so what is this megapascal? If you can convert this one to, look at this. Megapascal is, okay, so we will try to convert that meganewton, so that you will see meganewton or megapascal, not meganewton, megapascal. Okay, so let's try to convert that megapascal. Why do we need to convert that one? Okay, we should align the units, of course, for the cancellation to happen. So megapascal is equivalent to meganewton per meter squared, which is the original given. But later on, if this is what you will be using, you will end up with an area which is meter squared, which is a very, very small number. Why? Because we are considering a steel tube, which is that small. So you will end up with a meter squared area of that, which is a very, very small number. So it is better if you will express that one in millimeter. And the millimeter always goes with Newton, not meganewton, because meganewton in mm squared will be a very, very small number also. So we need to convert this in millimeters, and that also in a Newton. Okay, so convert this one. Okay, this is a simple conversion, guys. Okay, so 1 meter is 1000 millimeter. Do not forget to square that one, since we are converting squared meter. And then, okay, multiply to 1 meganewton, which is 10 raised to 6, that is mega, isn't it? Newton. This one is 1000 squared will be 1 million, or that is equivalent to 10 raised to 6, isn't it? Mm squared, and then this is meter squared cancels, meganewton cancels. So that is 10 raised to 6, 10 raised to 6. So you will end up here with 1 Newton per mm squared. Okay, so megapascal, therefore you can conclude that megapascal is 1 meganewton per meter squared, or that is equal to 1 Newton per mm squared. Okay. So this is what we will be using. So that 120 there, we will retain that one, but we can directly change our unit into Newton per mm squared instead of meganewton per meter squared. As you can see, that is the proof. Okay, that is the proof. So that's it. So we will be having now here, okay, that is 120 megapascal. Later on we will substitute that one, but in terms of Newton per mm squared, since we will be solving the area. So rearrange the given formula by the normal stress. Sigma, okay, is given, P is given. What we are trying to get is the diameter, which we can find in the area. Okay, so we'll try to rearrange. That will be area is equal to P over sigma. And then what is area? We can break this down so that we will try to bring out or expose the unknown. So that is actually the area of the ring. That's just the area of the steel ring here. That is the cross section. Okay. So how do we get the area of the steel? Is to get the area of the big circle minus the area of the small circle, which represents the hollow or the space. So we are using a diameter, so the formula is 1/4 pi diameter squared. Okay, so that is the big circle, and then minus the small circle, but your diameter is 100, so 100 squared will be 10,000. Okay, this is our A on the left side. Substitute that one. Your P is 400,000 Newton, and then your 120 is megapascal, but we need to change that one in Newton per mm squared so that the cancellation will happen. And then play around with this. Newton cancels. You will end up with 400,000 over 120 mm squared. And then play around with this. This is the simple algebra, guys. This is our unknown. So cross multiply that one. Transfer. This will become plus. And then that will be ending up with 14,244.13 mm squared. But that is the squared. So what we need is the diameter. So get the square root of both sides. Eksakto magiging. Your mm squared will become millimeters, which is 119.35. So what does that mean? That what we need is a hollow tube with inside diameter of 100 mm and outside diameter of 119.35 at least. But we can use a bigger diameter with this, because the bigger the area, okay, in our formula, look at our formula, the bigger the area, if I will try to increase the area by increasing the outside diameter, isn't it? If I will increase 119.35, then that will increases my area. And as the area increases, what happens with these trees? Okay, as the area increases, given P as the constant, this will increase, and then the entire value will decrease. So the stress will decrease as the area increases. Okay, so this is the required, so that we will not surpass the limit, the strength of the steel. We should have at least 119.35 outside diameter, but you can use bigger than that. Okay, so that's it. That is how we will solve the capacity. That's why we call this one strength of materials, or mechanics of deformable bodies, or in other term we call this one strength of material, because we are trying to determine strength of material based on stresses and then forces. Okay, because if we will be using this certain type of material on construction later on, then we need to understand how much that could carry. And that is the strength that we are talking about, and we are expressing the strength in terms of stress. Okay, and that is the first type, normal stress. Okay, second, let's try to have a second example here. Okay, so a homogeneous 800 kilogram bar AB is supported at either end by a cable as shown in figure. Okay, so shown in this figure. Calculate the smallest area of each cable if the stress is not to exceed 90 megapascal in bronze and 120 megapascal in steel. So we have here two types of support: a cable which is made of bronze and a cable which is made of steel. We have this length. Okay, we have this length, but actually that doesn't matter. What we will try to understand here is for us not to surpass or to exceed the given strength of the bronze and the strength of the steel. Okay? So, mas malakas yung steel kaysa kay bronze. So, how do we know that we are not exceeding that one? Of course, we will try to find out what are the forces acting on the bronze and steel. So that we will, what is the problem here again? Is smallest area. So that we will recommend the area to be used here in bronze and the area to be used in steel, the minimum area of this cable, so that that will not fail. Because if you will try to just give there a certain area, and then that is not enough to carry the stress, which will exceed the strength of the bronze or steel, then that will fail. Okay, so that is what we are trying to do here. So for us to investigate the stress on the bronze and steel, we should know the force that is applied on those. So again, this is simple statics. So cut this one, express, that will be in terms of tension force going away. So summation, you can take a moment here, or actually this will be equally distributed since that is a single force exactly at the middle. So 800 kilograms. Okay, we are on megapascal, so we should convert the kilograms in force, which is Newton or kilonewton. So the equivalent of 800, okay, multiply that 800 here, multiply that 800 to gravity, isn't it? Times 9.81, that will be 7848. Okay, 800 kilograms, multiply that one to gravity, which is 9.81, that will be 7848 newtons. Okay, so but first we should write down the given. So we have here a given mass, that is the mass that is being carried by the support cable and the cable support. So that is what we converted into force, which is, or weight, which will be distributed on the force on each cable. And then we have here a sigma. It means that is the stress or the strength of the BR. It means the sub BR is the bronze, sub ST is the steel. So those are the, oh sorry, it is a typo. It should be, okay, let's just change that one. That should be 90. Bronze is 90. Yeah. Okay, that is 90. Wait, let's just wait. Okay, let's continue. So bronze is 90 and then steel is 120. What is required? What is required is the area of the bronze or the steel, since we are trying to find the smallest area. Because of course we can actually give a big area for that to be enough to carry the stress, so that will not exceed the allowable. But of course, for example, we are on actual design. We are trying to design as much as possible. We will try to maximize the strength so that we will be ending up with less expenses. Okay, if we are on actual design. Okay, so again, that is just coming from the formula of normal. Why is it normal? Because again, the force is perpendicular. If you will try to cut the cables, the area is perpendicular to the force that is carried by the cable. So rearrange again, area is P over sigma, but we are first focusing on the bronze and then later on we'll go to steel. So what are the P? Again, as I've said, we need to convert the 800 kilograms into Newton, which is 7848. By symmetry, we can divide these into 2, or even if you want, you can apply simple statics. Get a summation of moment here, solve for the P on your bronze. Summation of moment here, solve for the P on the steel. Okay, that could be your solution. But since this is symmetrical, we can divide it by 2. Okay, you can prove that one. So each will experience 3924 newtons. That is the external force, but that will be the same as the internal on the cable, as I've said, since we are trying to satisfy equilibrium. So for the bronze cable, the area should be P over sigma of the bronze. So our P there is 3924. The strength of the bronze is 90 megapascal only. So the area required for that, okay, megapascal, you can change this one into Newton per mm squared again. So you will end up with an area of mm squared, which is 43.6. Okay, let's try to check again. 3924 over 90. Yes, 43.6. And for steel, what will just change there is since they have the same P, what will just change is the sigma. It will be now 120. So that will be 32.7. So for us, okay, to recommend, if you are the designer of this support, you will recommend for the bronze, if you are using a bronze, at least 43.6. If that is a circle, then you can, that is the area of the circle, so you can compute the diameter if that is in circle cable. But of course, that is the common shape of cable, circle, isn't it? So you can transform this one into a diameter if you want. But the question there is area, so let's give it as an area. So the area of bronze should not be less than 43.6 for that to be able to carry the load. And then for the steel, that should be 32.7. Okay, so why? If you'll try to compare, why are they different? Yet they are carrying the same amount of P, because they have different strength. The steel is stronger than the bronze, 120 compared to 90. So you will expect that even the steel is smaller, they can carry the same amount of load, even if that is smaller based on the area. Okay, that is the meaning of the area and then strength. Okay, so that is number 2. Let's have one more. Okay, so an aluminum rod is rigidly attached between a steel rod and a bronze rod, as shown in the figure here below. Okay, so aluminum rod is rigidly attached between steel and bronze. So this is the aluminum that is in between the bronze and steel. Okay, axial loads are applied at a position indicated. So actually you had this one on your statics. Okay, finding the resultant forces. If you try to investigate the steel, cut the steel, and then you want to get the resultant applied on or acted on the steel. If you want in the aluminum, cut within the aluminum, isn't it? That is statics. So find the maximum value of P that will not exceed a stress in steel, which is 140, that is the strength of your steel, aluminum, which is 90, and then bronze, which is 100 megapascal. So those are the respective strength of each type of material here on our composite member, and with the different types of loading. So, okay, if I will try to cut here, then I will try to bring out what I will try to expose what force the bronze is under, if that is tension or compression. But actually, it says there that that is the will not exceed. It means maybe that is the strength with respect to tension or with respect to compression. So it is not stated. So let's assume that this is both. If that is compression, then that is for steel, that is 140, even if that is tension. But in actual, okay, for example, in concrete, a concrete is strong when it comes to compression force. But when it comes to tension, that will easily rupture. So for example, again, a concrete is weak in tension but strong in compression. So there should be different strength within compression, strength within tension. However, since that is only single strength is given within the material, then let's assume that the compression strength and then the tension strength is the same. Okay, so cut the bronze and then summate. Okay, so this is the only force experienced by the bronze. So that is a compression, because that is going towards, okay, compression 2P. The reaction should be, the internal reaction of the bronze should be 2P, which is going towards. So that is a compression. Therefore, that is compression force. And then cut at the aluminum, then summate. We have there now an additional P, which is going to the right, summation. Okay, you can follow this one. You can follow this one, but that is just to explain. This is just simple statics. So cut this one, let's say summation going to the right, so P minus 2P plus the reaction P of the aluminum, okay, is equal to 0, since that should be equilibrium. Okay, you can follow this one. Then you will end up here, this will cancel, P will cancel one of that, so P of the aluminum is equal to a single P only. Okay, P is the force that we are trying to determine. This is twice the force P, 1 of the force P, 4 times of the force P. That is the meaning of that. Cut at the steel. Okay, so therefore this is going towards, so that is also compression. Cut this one within the steel, summate, then you will end up with resultant or reaction, which is for the steel 5P going towards, so that is also compression. Therefore, all the stresses, the stress in the bronze, aluminum, and the steel are all in compression. Okay, so again, for bronze that is 2P, for aluminum that is P, for steel that is 5P, all of them are in compression. So continuation, there's continuation here. So for bronze, we will try to rearrange. Again, formula is sigma is equal to P over A. What do we need? What do we need is the P, okay, the P, that is the unknown. So rearrange, your P is equal to sigma times A, or A times sigma. So the area of the bronze that is given actually, yes, okay, you're given here 200 mm squared. So 200 mm squared, megapascal is, you can transform that one in Newton per mm squared. So mm squared cancels, you will end up with a Newton force. So 2P, your P of the bronze is 2P. Okay, do not forget about that. That is the reason why we solved there the equivalent resultant force. Okay, so 2P, and that is area of the bronze 200 times the strength, since we are trying to limit ourselves within the strength. For bronze, that is 100. So the P that can be carried by bronze is the 10,000 newtons. That should be the value of the P here for the bronze to be able to carry that one. For aluminum, the same formula, area times sigma. So area of that is 400, and then the strength of that aluminum is 90 only. So multiply that one. 400 times 90 will be 36,000 newton. That is what should be the P that can be carried by aluminum. And for steel, the same, 500, since that is the area, 140 is the strength, that is 14,000. So that is the one that will be carried by the steel. So they have different values of P that can be carried by the different types of materials. But the question there is, within that value of P, all of this should be able to carry, okay? Or no material should fail within that value of P. So that is the question in the problem. That is the problem, okay? We should find the P wherein none of this material will exceed its limit, okay? So if your bronze can only carry 10,000, your aluminum can carry 36, but your steel can carry 14. Well, if you try to analyze this one, how is it that the aluminum is 36? Okay, compared to the steel, yet the steel is stronger than aluminum. That doesn't explain within the value of P, because as you can see, we have different types of forces that is carried by each. In your bronze, that is just 2P. In your aluminum, that is only P. That's why you ended up here with a big value of P, which is carried by the aluminum. In here, if you will multiply that P, which is carried by the bronze, bronze is 10,000 multiplied to 2. The bronze can carry a total of, the bronze here, okay, can carry 2 times P, 20,000 Newton. So still, aluminum is stronger than the bronze. But in your steel, wrong. Okay, different, because of course, different way. But for steel, that is 14 times 5, since that is 5P. That is what is carried by, okay. The other factor that affects here is not just the strength, also the area. Isn't it? Based on the introduction that we discussed, the area also contributes to the strength, not just the strength of the material itself. The area, okay, even if consider, okay, this is weak, but the area is very, very big, it can still carry, okay? So that is the reason why if you'll try to summate here, that is 2P, which is equivalent to 20 Newton, because the area is smaller to aluminum than aluminum. So we cannot compare P and the area alone, we will compare the strength, okay? So however, if that is the P that can be carried by bronze, and that is the P by the aluminum, and that is the P by the steel, then what should be carried by the entire composite material or composite member should be the least, okay? It means that should be 10,000. That is the maximum P that will be carried, so that none of this will fail, okay? Because let's say that is 14, I will apply that one. Yes, that the steel can carry that one, the aluminum can carry that one, but the bronze cannot carry, because the bronze can only carry 10. That's why, for us to be safe, for us not to exceed any of the capacity, then we should use the minimum. Therefore, 10,000. Okay? So again, based on our 3 examples, how do we categorize this as normal? Because the force acting on the material is perpendicular to the area that we are considering, okay? Just like here, the area is perpendicular to the force. And here, if I will try to cut, the area is perpendicular to the force. In here, we are trying to cut a perpendicular area to the direction of the force. That's why this is an axial or normal stress. Okay? So that's it. So let's review some concept of this unit. The internal resisting force is used in the computation of simple stress. Okay, that is the internal resisting force. However, again, what is given to us will be external. So all we need to do is find the member forces. So that is what you did on statistics, or I mean statics. Okay, you will try within the given types or system of loading, try to find out the force that is experienced by the certain member that you want to consider. Okay, just like in thrust analysis, isn't it? Member forces of thrust. So simple stress can only occur when stress is constant or uniform throughout the body. We can, again, as I've explained, the actual scenario is that the force is acting three-dimensional in different directions. But there are this type of stress wherein the direction of the force is a simple, perpendicular, parallel, and so on and so forth. So that it will give us a uniform stress on the area, okay, constant on the single area. Therefore, we can say that that's a simple stress. So that is our focus for this subject, simple stress. Okay, for normal stress, the force is always perpendicular to the cross-sectional area. Okay, so that is what you should keep in mind for normal stress. Okay, so if you have any question, you can comment below the video. We will be having a comment discussion there. Or if we can answer that, then we will be answering on the live meeting that we will be setting. Okay, that will be announced on your canvas and your announcement tab. Okay. So thank you very much for watching.